Now let's take a look at the growth of um, precipitate. In particular, for simplicity, let's take a look at the planar incoherent precipitate. Planar means the interface between the precipitate and the matrix phase is flat, okay, like a plane. And incoherent just means the interfacial energy between the precipitate and the matrix or the host doesn't it's a constant value and does not depend so much on orientation, which simplifies the treatment of the mathematics. Okay, so we say beta precipitate, as what we illustrate, grows into the alpha matrix through a incoherent interface, which means the interface is moving as what we illustrated towards the right hand side. Okay, and the following plot shows concentration with respect to location, and within the beta precipitate, the concentration is constant at x beta. Okay, within the precipitate beta, the concentration is fixed, and within the host of or matrix of alpha, the concentration may have different um, scenario or change with location. For example, the concentration within the alpha matrix may be flat and be the constant of the original concentration x0. This would be the case for so-called interface controlled scenario, which means within the diffusion of alpha phase, within the alpha phase, the diffusion is very fast, and the alpha phase, the concentration is constant. The diffusion is very fast, while at the interface, the transformation between beta and alpha is slow, and in that case, we would have constant concentration within the host or matrix material. On the other hand, more likely, we may have a concentration profile that follows this red dashed line as what we draw here. Within deep of the matrix phase, the concentration is still x0 or the initial system concentration. But right at the interface between the beta and the alpha, again, this is represents the interface between beta precipitate and alpha matrix. Right at the interface, the alpha concentration is approaching the equilibrium concentration as determined by the equilibrium phase boundary, the intercept between the isothermal temperature line and the phase boundary line. Okay, so locally, right at the interface, within the alpha is xeq, the equilibrium concentration. But the concentration gradually changes to the initial or host matrix concentration. This will be the scenario called diffusion controlled. Okay, the concentration profile. And between these two extreme cases, there may be a scenario as illustrated by this green profile. The concentration is at the interface somewhere between um, host or matrix original concentration x0 and the equilibrium concentration. That will be so-called mixed controlled. Okay. So for most solid state precipitation or solid state phase transformation, the concentration would be so-called diffusion controlled. And in those conditions, the precipitate growth process would also be determined by the diffusion process. Diffusion of what? Diffusion of solute from deep within the matrix to near the interface. Okay? And if that's the situation, as what we mentioned, follows the red dashed line for diffusion controlled for the concentration profile within the alpha matrix. Okay, if that's the case, Then, as we mentioned before, right at the interface, we have local equilibrium, which means in the beta phase, the concentration is X beta, while on the matrix side, the concentration is determined by Xeq, the equilibrium concentration. Okay, and then in this scenario, the solute atom would diffuse from deep within the matrix, deep in the matrix to the interface. As you see here, deep in the matrix, the solute concentration is actually higher at X0, while right at the interface is Xeq, which is lower. So the solute has a tendency to diffuse from high concentration um, in the matrix at X0 to low concentration of Xeq right at the interface. Okay, and then the growth rate of this beta precipitate, would be determined by the diffusion of the solute atom to this low concentration region. That controls the precipitate growth or the movement velocity of the interface between the beta precipitate and the alpha matrix. Okay, under such a scenario, if we consider the balance of solute atom flow, the solute atom will diffuse from deep of the matrix to the interface, and then right at the interface, if it goes through the alpha to beta phase transformation, the solute has to go into the beta phase. Then if we consider the balance of flow, then the diffusional flux into the interfacial region would be D times the concentration gradient. Okay, again, D is the diffusion coefficient, dc over dx is the local concentration gradient, and this term would be the flux of solute atom into the diffusion region. Okay, and on the other hand, when I have solute atom here, then I have phase transformation from alpha to beta. The transition of the solute atom from alpha phase into the beta phase would be equal to velocity times the concentration difference of C beta, the concentration of solute atom in beta phase, minus the concentration of B atom under equilibrium, okay, which is related to Xb and Xeq. So if we consider these two, then we would have a balance. The flux of solute atom into the interfacial region would be the same as the transition of the solute atom from alpha phase to beta phase. Okay, velocity times the concentration gradient. You may wonder, is this true? So let's check the unit. On the left side, we have the unit of flux, which means per molar of atom per unit area, which is meter squared per unit time per second. On the right side, the unit would be velocity, which is meter per second, times concentration, which is molar per meter to the power of 3. So meter for velocity and the meter per cube cancel. So on the left side, the net unit would be molar per second per meter square, which matches the unit on the left side. So at least you rest assured the equation here that we wrote for the balance of mass for the solute atom holds. Okay, the left side is flux, how fast it flows from deep region in the matrix to the interfacial region would be matched to the solute atom moving from the interfacial region into the precipitate. Okay, at the same time balanced, accompanied by the motion our movement of the interface with velocity of v. Okay, and if we rewrite this equation, we would have the velocity of, which is dx over dt. The first derivative of location with respect to time would be velocity would equals to left side d, move the difference in concentration C beta minus CEQ to the denominator and keep the dc over dx. Keep the dc over dx. So this tells us the velocity of dx over dt, how it relates to the local concentration gradient. Okay, and this is what we have: the velocity of the interface movement, how it links to the local concentration gradient. And again, D is for diffusion coefficient. Cv means the concentration, number of mole per unit volume, minus the equilibrium solute concentration, times dc over dx, that is the local concentration gradient in the matrix near the interface. Okay? And if we, for simplicity, assume the linear concentration profile in the matrix phase, in the alpha phase, near the precipitate, what we mean is that, as we plotted here, we are plotting concentration versus horizontal axis for location, and then left side is beta phase, right side is alpha phase. Within the beta phase, we have a constant concentration of C beta, but then within the alpha phase on the left, we, for simplicity, assume, as we mentioned, linear concentration profile. Right at the interface, it's CEQ for equilibrium concentration, while deep within the matrix is C0, or the host system original concentration, and is following a linear profile, which means the concentration changes linearly with respect to location. And if this depleted region has depth or thickness of L, then the delta C 0 is a concentration difference between C0 and CEQ. Okay, we have linear concentration profile. Then the balance of solute atom would give whatever is missing on the matrix side, which are represented by the green area, would be the same area as the blue area on the beta precipitate. The balance of solute would give something like this. X is the precipitate thickness or beta phase thickness. Thickness times C beta minus C0. C beta minus C0. That's the difference in the precipitate and the matrix. This blue square area would be equals to the green triangle area, which is half of depth times the gap, which is the concentration difference. Okay, then the concentration gradient in the matrix, which is dc over dx. dc over dx can be simplified just as the slope, which is, as we illustrated here, delta c0 divided by L, the thickness, right? This relationship relates the local concentration gradient. It's essentially, if it's simple linear, it's just a delta C over the thickness for the local depleted region within the matrix. Okay, then the precipitate growth rate, which again is the V or dx over dt, we are going to rewrite it as V equals dx over dt, and we keep the first term, diffusion coefficient, divided by the difference in Cb minus CEQ times dc over dx. For dc over dx, we are going to write it instead of using the linear approximation as delta C0 divided by L. So for this equation, we are essentially replacing the concentration gradient term by this delta C0 over L term, okay, because of the simple linear concentration profile within the matrix that we assumed, okay. And then if we look at the balance of absolute mass relationship, we can see that delta C0 can be rewritten. So for this equation, the first term before the dot, before the product, we keep B divided by CB minus CEQ we keep, and delta C0 we keep. But then this length L from this, the second equation from the top that we get, L from this equation would be 2 times the left side divided by delta C0. So we replace L, the thickness for the diffusion as 2 times the difference C beta minus C0 times X divided by C0. So this simplifies the relationship and gives us the velocity. And we do a combination. We put delta C0 in the denominator with the delta C0 at the top. So we get D we keep in the numerator, and delta C0 and the delta C0 combined, we get delta C0 square, and 2 we keep, C beta minus CEQ we keep, and C beta minus C0 we keep, and X we keep on the denominator. So in this way, we get a relationship for the velocity for the precipitate growth, or the velocity for the interface to move between the beta phase and the alpha phase. Okay? So this is our velocity equation, assuming linear concentration profile, assuming diffusion control. Okay? And then we rewrite the velocity equation here, and if we rearrange this equation a little bit, we are going to have dx and x and the 2 combined, 2x times dx, 2x times dx, and then we are going to move dt to the right side. So this is what we have, d times delta C0 square divided by the products of the two concentration difference times dt. And then if we have this, we do integration on both sides, left side and the right side. Okay? Left side we integrate, we get x squared, and the right side, if we assume d is constant and the delta C0 is constant, and these two differences are also constant, then we would get this just the t. And assume for simplicity there's not too big change in the matrix concentration from the initial concentration to the equilibrium concentration, which means the two difference C beta minus C0 can be approximated as C beta as equilibrium concentration. Then, if we consider another factor which relates the molar fraction xb, which means the molar fraction of B atom with respect to the total A and B relates to the local beta concentration times Vm for molar volume. Okay. The molar fraction is equals to local B concentration by volume times the molar volume. To check the validity of this one, the Xb has a unit of molar over molar, which is essentially unitless, while Cb has a unit of molar per meter cube, while Vm, which is The volume has a unit of meter cube divided by molar. So meter cube and the meter cube cancelled. So on the left side we have molar, right side we have molar over molar, which is essentially unitless. So you understand this relation that relates the molar fraction of B atom, okay, which is B number of B atom divided by total number of atom. On the right side is number of B atom per volume, and then molar volume is the total volume but divided by the total number of atoms, A plus B. So of course these are the same. Based on this relationship, we are going to rewrite our equations. Left side we keep at x0, x square, the location square, but right side we keep d, we keep t, but then the every c term we times the Vm term, and then we would change to molar fraction. Delta C0 changes to delta X0. C beta minus C equilibrium become X beta minus X equilibrium. Okay, for this one. And then if we take the root square root, left side we get X, and right side we would simplify to this one. Delta X square become delta X. This bracket square become X beta minus XEQ, and the dt term becomes square root of dt. So what essentially this tells us is the interface location with respect to time would follow parabolic law, or in another way, the thickness of the precipitate during this precipitate growth process would follow parabolic law, which is typical for diffusion controlled process, and which is the assumption that we made in the beginning. And then, based on this location with respect to time, if we take first the derivative, we can have the velocity for the interface movement, or the velocity for the precipitate growth would be keep the first term, keep the diffusion coefficient square root of diffusion coefficient, but square root of t becomes 2 times 1 over square root of t. What essentially it means that the precipitate growth rate would decrease over time. That's kind of the conclusion that we got. After doing this long derivation, we found out the precipitated growth would follow parabolic relationship, which is consistent with most diffusion controlled process. I square equals dt times a constant, while x equals square root of dt, and the velocity, the motion of the interface would decrease over time, which means as the time goes on and on, the precipitate growth, linear growth rate becomes slower. Okay?